First, we should all welcome back our conquering hero, since Rebecca was part of the team that took first place, right? In a leadership exercise of some sort. I understand it's like a simulation of what do you do in this, crazy situation. They won. Yay. Congratulations. We're all so proud of it. Oh, and she's got the... A reminder that the posters in electronic form are due by 3 p.m. on Friday. That's when I have to make sure that Dr. McNeil has them, and she will be delivering them to UNL to be printed. So I have no control over that deadline. So just a reminder about that. I ended last class period talking about Werner Heisenberg. I started talking about the nuclear bomb and everything, and forgot that the point here was Werner Heisenberg was the Oppenheimer of Germany. He was leading their project. Because he led their project, his, shall we say, significance to Western science dropped way off. So brilliant scientist that he was, he permanently alienated himself, as you can see, from most of the scientific community because he was working on the German bomb. Not so with those working on the American bomb. For instance, Albert Einstein, I believe, was working on the American bomb. I know Richard Feynman was the youngest person working on the American bomb. Many great scientists in the Western world. I think it probably goes down to the fact that the United States was on the winning side. The winning side scientists kind of shunned the losing side scientists. But Werner Heisenberg is the person who came up with the uncertainty relation that we talked about last class period. The uncertainty relation being that there is a certain product between the uncertainty in position and uncertainty in time. This diagram here is illustrating how we can actually calculate that with wave packets. Now, wave packets is way beyond this class, okay? I'm not expecting you to be like, oh yeah, I understand that. But the ideas are kind of simple. If you send a pulse of light, that pulse of light is a packet. So the picture on the left is a packet that's a pretty short pulse. Okay, your left, yes. The picture on the right is a packet that's a longer pulse. Both of those are what we call wave packets. The packets contain waves. And if you look at that, you would say, well, they're both the same frequency of light. That is, the number of cycles per second are the same. But technically, they're not. Technically, to make that packet, you have to have more than just the one frequency. You have a range of frequencies. And the smaller the packet, the bigger the range of frequencies are that you have to have. And you may at this point be saying, yes, this is getting me nowhere. But it is. Because the frequency, of course, is inversely proportional to the wavelength. So that means you have a range of wavelengths. The one on the left, the small wave packet, has a large, broad range of wavelengths. The one on the right has a much narrower range. But we learned that for light, momentum is h over f. Or not h over lambda, or equals h f over lambda is equals c over f, yeah. hf over c. So this one here has an uncertainty in frequency. Now, this is not showing frequency domain, so it's not domain to domain. But it has uncertainty in frequency, which means it has an uncertainty in the momentum of the photons. There's also an uncertainty in position, and the uncertainty in position is what we actually see here. We'd say here's the position of the wave packet, and the uncertainty in position is going from one edge of the wave packet to the center. So the one that has the narrower packet, a smaller uncertainty in position, has a bigger uncertainty in frequency, and thus a bigger uncertainty in the momentum. And so Heisenberg was able to show that when you multiply the uncertainty in position by the uncertainty in momentum, it's always greater than or equal to, and where did I have it? Must have been up here. I must have erased it. uncertainty in position times uncertainty in momentum is always greater than or equal to h bar over 2. Somebody remember for me? I do. What is h bar? What does that stand for? Planck's constant over 2 pi. So that's what Planck was able to show. So that picture of the wave packets is giving you an idea of where it comes from. This picture here is showing not a packet, but uniform waves. The uncertainty in frequency here is 0. So the uncertainty momentum is 0. But where is the light located? No idea, right? It could be anywhere in this range. We're going to say, where's the photon associated with this? I can't identify. It's got a really big uncertainty position. So that's what plays in here. The more precisely you know the momentum, the less precisely you know the position. Hence the joke about Heisenberg driving his car, gets pulled over by a police officer, and the police officer says, "Do you know how fast you're traveling?" Heisenberg says, "No, but I know exactly where I am." The police officer says, "You were traveling 60 miles an hour." And then Heisenberg, exasperated, says, "Great, now I'm completely lost." Yeah, man. We physicists have great senses of humor. Never believe anything to the other. Yeah. It's a funny joke. The joke goes on. Schrodinger's in the car with Heisenberg. The police officer says, "Can you pop your trunk?" And so Heisenberg pops the trunk. He goes back and looks and he says, "Do you know that you have a dead cat in your trunk?" And Schrodinger says, "I do now." Yeah, we're full of great jokes. Just wait till we talk about those quarks. You have the up and the down because they had the first two and they had to choose opposites of some type, plus and minus, north and south, up and down. But then they found that there were some particles that behaved strangely. And so they said, well, there must be a particle that's causing this. Let's call it the strange particle. So we have the strange quark, also called the sideways. And then their theory said that there had to be a fourth one to go with the strange that was the opposite of the strange. And they said, well, we can't find it, so it leads a charmed life. And they call it the charm particle. I'm not lying about this. Then they determined that there had to be two more. And so they said, well, let's find two more opposites. And they said top and bottom. And some people said top and bottom is really boring. Here we have strange and we have charm. And so top and bottom have alternate names of truth and beauty. See, that's okay. You guys don't care. It's what?
Scientists are quirky.
Quark, by the way, is a nonsense word that comes from James Joyce's book, Finnegan's Wake. Yes. I know you said quirk. Well, you were making a joke on quirky, but I had to go with, yes, it is indeed quirky to take a nonsense word from Finnegan's Wake to name the particles. This here is an example of applying Heisenberg's uncertainty principle. I'm not going to do the problem here today, but the problem is if I have particles or waves going through a slit, we know that you're going to have them spread out. And so we're going to have some uncertainty in position here. 2 delta x is the size of the slit because we say, okay, it's going through the center with an uncertainty of 1/2 the width of the center. And then we can calculate the uncertainty momentum by saying it has, this is my momentum and this is my uncertainty in the momentum. And using the equation for the first diffraction minimum, we can then calculate what the uncertainty momentum is with relation to the uncertainty in position and get a relationship, an uncertainty relationship based on the diffraction. Like I said, not going to do it. There's the problem. The uncertainty relation is not just a relationship between momentum and position. You can find uncertainty relationships between any two observables whose operators don't commute. Most of those words made no sense to you. One prime example is between energy and time. And it turns out that the uncertainty relationship between energy and time is the same as the uncertainty relationship between position and momentum. That is, the uncertainty in energy multiplied by the uncertainty in time is greater than or equal to h bar over 2. Why in the world is that important? Well, scientists, when they're doing particle physics experiments, they're looking for particles that have very, very short lifetimes. And so how do you determine the lifetime of a particle that's really, really short? What they can measure is the energy released when it decays. And when they look at the energy released when it decays, they don't just find the peak and find the average value for the energy. They find how wide that peak is and get the uncertainty in the energy. And then using this relationship, since they know what the uncertainty in the energy is, they can get a limit for its uncertainty in time for how long it existed. And so they get the lifetimes for these particles by looking at the uncertainty in the energy. So the lifetime of the particle is approximated as Planck's constant divided by 2 times the uncertainty in the energy. So the bigger the energy peak, the bigger the uncertainty in the energy, the shorter the lifetime for the particle. So it's used in a very regular fashion in particle physics. Oddly enough, it's also used to explain the Casimir effect. The Casimir effect is I can have a chamber that's in complete vacuum, and suddenly, inside that chamber, a particle and an antiparticle will appear out of nowhere. That is a violation of conservation of energy. But the physicists say, that's okay. We can violate conservation of energy as long as the duration of the violation is shorter than what we have with this equation. Because we have the uncertainty in energy times the uncertainty in time, it has to be greater than or equal to this. If the product of the uncertainties is less than that, as far as we know, there was no violation. And so that's how they can justify the Casimir effect can occur. Now, oddly, the Casimir effect is used by some to posit how the universe began. That you could conceivably have something as energetic as our entire universe produced by something like this. But it's the likelihood is proportional to the lifetime, and the likelihood of that would be very, very, very close to 0. Like so close to 0 as to never be distinguishable from it. Okay. Getting back to quantum mechanics. All of this is in the quantum mechanics realm that I've been talking about. Quantum mechanics I talked about in class on Friday, the wave function. And the wave function, as we calculate the wave function from a wave equation, the Schrodinger equation, we find that we have energy levels that sometimes are quantized, only certain energy levels. Now, the energy levels will be quantized if there is a constraint on where the particle can be. If the particle can be anywhere, it can have any energy. But if it's restricted in where it can be, it's going to turn out that it has quantized energy levels. This makes life interesting because virtually everything is constrained to being in a certain location. So for instance, when you're swinging in a swing, you tend to believe I can have any energy I want, which means I can swing any height I want. But quantum mechanics says, no, because you're confined, you have to be here on the swing. You can't be somewhere else. You can only have certain energies. So when you're in the swing, you can only have this energy or this energy, but nowhere in between. That seems bizarre, doesn't it? Go back to the quotes I gave you, and I think one was from Richard Feynman saying that if you're just willing to accept that you can have these weird results, you'll find that life is really interesting and mysterious. Yeah, skip right past that. Particle in a box. If you want to learn about the particle in a box, come to class tomorrow. At 11:30, we will be doing the particle in a box problem. The particle in a box problem is a potential energy that is infinite outside of the box and zero in the box. We call it a particle in a box because if I have a box, I have no potential energy inside, infinite outside, I'm never going to have enough energy to take a particle that's inside the box and get it outside of the box. So it's contained, it has to be in the box. But because it's in the box, what does that tell you? It's quantized, it's going to have quantized energies. And so this particle is going to have quantized energies. And if we were to think of this like a wave on a string is in fact a good analogy to a particle in a box. And a wave on a string likewise has quantized frequencies, which for quantum mechanics would mean quantized energies. So the particle in a box can be thought of as an analogy to a wave on a string, and you can have energy 1, and believe it or not, this is the solution to the particle in the box. Energy 1 is a half a wavelength fits in the box. Energy 2 is a full wavelength fits in the box. Energy 3 is 3 halves fit in the box, and so on. So you have very specific wavelengths, which results in very specific energies for the particle in the box. So this is the equation that we're going to find in class tomorrow, gentlemen and Gila. For the particle in the box, we'll work through it carefully. One of the interesting outcomes is the particle cannot have zero kinetic energy. Is that interesting? Well, to me it is. That's saying if I have a tall box and I toss a ping pong ball in there, that ping pong ball can never come to rest. It always has to be bouncing. Not possible to come to rest. If I reach in there and try to force it to rest, I can't. It's got to be bouncing. That's what quantum physics says. Now, this has an important implication when we get to talking about temperature and absolute zero. What is the layman's definition of absolute zero?
Negative 273.
Okay, that's a number. Negative 273.15 Celsius, or 0 degrees Kelvin. But since temperature is a measurement proportional to the average kinetic energy, the layman's definition in terms of kinetic energy for absolute zero is zero kinetic energy. But quantum mechanics says that's not possible. So quantum mechanics says that absolute zero is the minimum possible kinetic energy, which is not absolutely zero because it's not possible to get to absolutely zero kinetic energy, which is bizarre again. Right? This quantum mechanics outcomes seem weird. And yet, as I told you on Friday, we have lots and lots and lots of tests of quantum theory that show that it gives us correct predictions. And so we believe these things because it gives us correct predictions. I just want to move past this. A very important thing that I think I already mentioned about quantum physics, it's probabilistic. Quantum physics can tell us the probabilities of something. It can't tell us exactly what's going to happen. Who had a problem with this? All of us should have a problem with this. The basic thinking that I had when I was in college was, if I know the position and the momentum of every molecule in this room, I should be able to calculate what's going to happen at any instant in time in the future because I can calculate the collisions and so on. There is a physical problem in that I don't have the ability to track them all and do the calculations and measure carefully. So I can't do it, but in theory I should be able to. That's what we call deterministic. You can determine what's going to happen if you have enough information. Probabilistic means you don't know, and there's no way of knowing. No matter how much you know about the current state, you can't predict the future. You can predict probabilities of the future, but not what's going to happen. By the way, chaos theory is between the two. Chaos theory is a deterministic system, a system where if you have all of the right information, you can calculate exactly what's going to happen. But it's so complicated that if you're off by 1 part in 10 to the 20th, you're not going to be able to predict what's going to happen beyond a couple hours or something. That's the way our weather is. Our weather is chaotic because it's so complicated. Even though if we knew every molecule's position, momentum exactly, we could predict exactly the weather, it's impossible for us to have that knowledge. And thus, it's chaotic. We can make predictions into the future, but they're going to fall apart as we get farther away because we don't have perfect information. But quantum physics is probabilistic. You can't do that calculation with quantum mechanics. It's just not an option. Who had a problem with this? Einstein had a problem with this. Was Einstein a dummy? No. Was Einstein bad at math? No. He was really good at math. He just didn't like math. He was trying to solve problems that no one to this day has ever been able to solve. I mean, that would frustrate all of us. So I would make statements about my difficulties with math too, because I'm trying to solve stuff and I can't do it and feel like an idiot. So Einstein simply did not believe, hence the quote I talked about last class period, God does not play dice with the universe. I quoted that last class period, right? Some say no, some say yes.
You did it. 51 to 52.
Oh, I did 252? Okay. Well, that quote is Einstein saying, I don't believe that nature really is probabilistic. I believe it's deterministic and we just don't understand it right. Quantum physics still adheres to, no, nature really is probabilistic. And so this brings us to the Schrodinger cat, the second part of the joke I told at the beginning of class that is so hilarious. Schrodinger's cat is an example to illustrate how silly this idea is. So the idea of the Schrodinger cat, I should have brought in my quantum textbook. My quantum textbook has in the front cover a picture of the live cat and in the back cover a picture of the dead cat. Where did I put my stylus? Here's the problem with walking around. So the Schrodinger's cat says, we're going to make a box. And in this box, we're going to put a cat. Okay, everybody just bear with me. That's my cat, okay? Good enough? And we're going to put a radioactive sample. Here's my radioactive sample. Now, my radioactive sample contains one atom. One atom that's radioactive. And that one atom is put in a detector that's a perfect detector. This is a Gedanken experiment. It's a thought experiment, not one that we're actually going to do. Nobody's going to do this to kill the cat. Okay? But we have a perfect detector that's going to detect when that thing decays. And when it decays, the detector decays it, or detects it, and you have in here a hammer. And you have a vial of cyanide. And when the detector sees that it is decayed, it drops the hammer. Hammer hits the cyanide. Cyanide vial breaks open. Cat breathes in the cyanide. Cat dies. Everybody understand this? We don't do this. We don't kill cats. You don't need to call the Humane Society. But what this is illustrating is the ridiculousness of the notion of this probability thing. Because quantum physics says that when I start this experiment, my atom is in a superposition state. That means it's in two states at the same time. It's 100% probability of being in the undecayed state. The atom has not undergone its radioactive decay. And it's 0% in the decayed state, having undergone decay. But as time passes, the undecayed state is dropping, the decayed state is rising. So after one half-life, the time when you have a 50% probability of it being decayed, you're in a superposition state that's 50% in the state that it hasn't decayed, and 50% in the state that it's decayed. Now, when you're talking about just with the atom, you're like, okay, sure, what does that mean? But if you look at the actual whole thing, if it's decayed, the hammer's dropped, the cyanide is broken, the cat has died. And so that means that when we've reached that one half-life, the cat, by extension, is 50% in the state of being fully alive and healthy, and 50% in the state of being dead as a doornail. It's not sick. it's 50% alive and 50% dead. And if we wait longer, we might have the cat is 0.1% alive and 99.9% dead. This 0.1% just as alive as can be, happy and purring. And 99.9% dead as a doornail and decaying and smelling. Quantum physics says it's going to remain in the superposition state until I make a measurement. When you make a measurement, you change the system. We talked about this. Actually, somebody brought it up when I was showing the polarizers. When you put that polarizer in the middle, it changed the state. If you check on the cat, and the cat's alive, boom, it's now 100% alive and 0% dead. If you check on the cat and the cat's dead, it's now suddenly completely dead. And so if you check on the cat and it's alive, you just start your timer over. It's now 100% alive and wait one half-life, and it's going to be back to 50% fully alive, 50% fully dead. And so when does the cat die if you don't check? It never fully dies. It's always a little tiny fraction fully alive and healthy. And if you open the door and look at it, it could be healthy and you go on. You know the odds, if you check in the door 2 days later and it's a half-life of half a second, the odds are that it's dead. But it could be alive, and you force it to be dead when you check. Hence why Schrodinger gets so upset when the police tell him there's a dead cat in his trunk. Because the cat wasn't 100% dead. It was a fraction of it was alive and healthy and purring until the policeman checked. That's the guy that you should call the Humane Society on. So the Schrodinger cat is to illustrate really how mind-bending these quantum physics ideas are. And it all has to do with this probabilistic nature that we now understand nature is. Fundamentally, nature is probabilistic. We can't predict exactly what will happen. Hydrogen atom. I'm going to talk about the history of the hydrogen atom here, starting with Democritus. I'm pretty sure I talked about Democritus before. Democritus said, if I take a sample and I break it in half, I'll have two smaller samples of the same thing. And I cut it in half again, I'll have smaller samples. If I keep going, I should get to some point where I can no longer break it in half. At that point, I have the smallest indivisible unit that I'm going to call indivisible, or in Greek, an atom. And so we have the atomic theory back there from Democritus. Now, Thomson, I think it's J.J. Thomson, discovered that matter contained electrons with the cathode rays that we talked about earlier. That is, putting a voltage difference, he was able to have electrons come flying out of a piece of metal. And so he deduced that matter must have electrons in it. And so he came up with the plum pudding model that said matter must be this goo of positive charge. So there's positive charge that's just spread out everywhere. And then you have these little raisins of negative charge that are the electrons. So that's the plum pudding model. Or as I like to call it, the oatmeal and raisins model, because that makes more sense to my life. And so then we had Rutherford's tinfoil experiment. I believe I talked about this, the experiment actually done by Young Marsden, where they shot alpha particles, little particles that we understand to be nuclei of helium atoms, 2 protons, 2 neutrons. They expected the mass of an alpha particle so much more massive than that of an electron, that if it hit an electron, it might slow down just a smidge. But essentially, the alpha particles would just go straight through. They just might be slowed a little bit. And what they found instead was some of the alpha particles bounced straight back at them. And I talked about this, right? His analogy that it was as surprising to them as if they had taken a piece of tissue paper, put it in front of a cannon, and fired a cannonball at that tissue paper. And when the cannonball hit the tissue paper, it bounced back at them. That is how shocking it was to them, because they thought this thin foil, it should just go right through. And so Rutherford said, well, this model is clearly incorrect. There has to be something that's really massive for the alpha particles to bounce off of. And in fact, Rutherford was able to do experiments and determine that in that gold, there was a positively charged nucleus, and he was able to determine its size. And so Rutherford said, okay, we have that positive nucleus. We must have electrons orbiting around the nucleus like planets orbiting a star. And so he called this the Planetary Model. Now here's a very sad admission. When I was in high school and I took physics class, that's what I believed. I didn't understand my teacher. Talked about electrons doing circular orbits around the nucleus. That made sense to me. The rest of it didn't make sense to me, and so that's what I stuck with. Well, right away, there was a lot of experimental evidence to say that's not right. It can't be right. For starters, we just learned about Bremsstrahlung radiation. What caused Bremsstrahlung radiation? Remember in the X-ray spectrum we had the Bremsstrahlung? That was the characteristic. The characteristic peaks were caused by electrons falling to the core levels for different kinds of metals to get different characteristic peaks. The Bremsstrahlung is the continuous part. Bremsstrahlung being a German word. Anyone here speak German? Sprechen Sie Deutsch?
Is that what the photons go straight through?
Bremsstrahlung is braking radiation. It's the radiation produced when you have a charged particle accelerating. In the case of the Bremsstrahlung, it's accelerating from going fast to not so fast. And whenever you have a charged particle accelerating, it gives off radiation, which means it loses energy. So if I have electrons, charged particles, doing circular orbits, they have to be giving off radiation. In fact, electrons should fall into the nucleus in less than a nanosecond if this model was correct. So it's very clear that this model has some flaws. So Niels Bohr came over to work with Rutherford, and Niels Bohr came up with his quantum model. So we'll go to the Bohr model. The Bohr model. Niels Bohr said, number one, we have steady state energies. Now I said number one. I might have my order of these things. Steady state energies. That is, the electrons can only have this energy or this energy, but no energy in between. That's a quantum hypothesis. He's proposing that the energy levels are quantized. And because these energy levels are quantized, it makes radiation impossible. Radiation impossible because that would be a continuous drop in energy. But you only have this energy state and this energy state, so you can't have that radiation produced. Now, that to me is a little troubling, because I like my laws of electromagnetism to agree with my laws of quantum physics. And this is saying the electromagnetism law just isn't allowed to work because it violates the quantum physics law. I think there's more to be learned there eventually. Then he also said the angular momentum is L sub n is equal to h bar n. Now, angular momentum, we remember linear momentum is mass times velocity. Angular momentum is radius cross momentum. So angular momentum is mass times velocity times radius if they're perpendicular. And so he said that the angular momentum is quantized. You can only have certain values for angular momentum. You can have 1 times h bar, 2 times h bar, 3 times h bar. You can also have, well, that's what he came up with for his quantization of angular momentum. So that's his true quantum hypothesis, because that's the one that's setting what is quantized exactly. And then he says that they're doing circular orbits. And there's one final piece of information. The absorption and emission spectra are from electrons jumping. For absorption, it's going to be up. For emission, down. Between steady states. That is, if you have an electron that goes from n equals 3 to n equals 4, its energy jumped up. Well, energy has to be conserved, so you must have had some light came in with exactly that energy that was absorbed. Or if you have an electron go from n equals 4 to n equals 3, then it's going to emit energy with exactly the difference between those two energy states. So that's Bohr's model. Bohr's model has some grand successes. For instance, it predicts exactly the Balmer series. Remember when we brought out the lamp and the glasses and we saw the specific lines of colors in the tubes? Please remember that? Yeah. It was for the hydrogen atom, the Balmer series, the visible lines we see, were exactly explained by this. A grand success, but also some grand failures. Grand failures in that, according to Bohr's model, the intensities should, have a nice continuous range, not this one's bright, this one's dim, this one's bright. And furthermore, when you put these things in a magnetic field, you see them split up. And in fact, even without a magnetic field, you see some of them split. And this can't explain that at all. So it had some flaws. So very quickly, Bohr's model was further modified to the model we have today, which is the quantum model. And the quantum model gets rid of Bohr's angular momentum quantum condition, gets us some different quantum results. So I'm going to only summarize here. The Bohr model says energy is equal to energy 1 over n squared, where energy 1 is equal to minus 13.6 electron volts. By the way, I know now is a bad time to remember this. I did not add a new homework assignment for tonight because I did not cover any more material last Friday than what was already in the homework assignment that was due Friday. So I did not add a new, in case anyone's wondering about no homework for tonight. Did everybody finish the homework on Friday? If you did, let me know, okay? Because I know you probably don't want to say in class, oh yeah, me, I didn't do it. I didn't. Right. Okay. So that is an important outcome from the Bohr model. Another important outcome is the radius, the Bohr radius, which I'm actually not going to write. This here was experimentally confirmed. So as we move forward, we better preserve this because that's an experimentally confirmed result. We need to find a way for it to be confirmed. So let's get to our quantum model. Our current quantum model throws away, okay, let's go back here. Our current quantum model throws away this, Angular momentum is quantized, but that's not it. So it throws away those two pieces. keeps the others. What do we do for that quantum model? Well, one is we can actually use the de Broglie wavelength and show that Bohr's results are the result of having an integer number of de Broglie wavelengths on the circular orbit. Question, Edika?
So there's angular momentum.
Uh-huh.
So that is all of it canceled, or just like we still have
The equation. Angular momentum is still conserved. Or not conserved, but quantized. But I mean, here's the new rule. Angular momentum squared is equal to, angular momentum is equal to h bar times square root of L times L plus 1. That's the new quantization rule.
It's just the formula that canceled that.
Just the formula, right.
Okay.
So it's a different quantization rule. So this picture is illustrating where we're likely to find the electron. Got rid of the circular orbits. I did cross out circular orbits, right? Yeah. Got rid of the circular orbits. We do not know the path the electron follows in an atom. So if you have an s orbital, everybody knows the s orbitals are those big spherical orbitals, right? That is saying this is where we're likely to find the electron. It says nothing about its path. The big frustration that led Heisenberg to his quantum physics development was that we can't determine what the path is for the electron. And so he said, forget it. I'm not going to worry about its path since we can't know it. I'm just going to worry about the things I can measure, like its angular momentum. So we don't know its path. For all we know, the electron could just be going, hanging out right there. Or it could be going, we don't know. We have no idea what its path is. So that's a big part of the new quantum physics. The wave function looks something like this. That's the wave function is a function of radius. The wave function is getting smaller as you go out. We learned from our analogy between light and the wave function that the probability for the position of the particle is proportional to the wave function squared. Now, one of the interesting things here is we have a spherically symmetric distribution. So if I want to find the probability of being at some radius r, I actually need to multiply by the area of the sphere of that radius, which is 4 pi radius squared. So what I really need to do is not graph psi, but I need to graph psi mod squared times 4 pi radius squared, which I'll bet you is right. Well, here's the two put together, the psi mod squared and the 4 pi radius squared. If you multiply those together, you get this. And it turns out that the quantum mechanics model gives exactly the same most probable radius as the Bohr model gave for the radius, which is a really cool outcome. For my quantum physics class, that's one of the two things they have to calculate. They have to calculate the most probable and the average radius. Given this distribution, where would you find the average? If probability is on the vertical axis and radius is on the horizontal, where's the average going to be? What I'm looking at is it going to be the same place as the most probable, shorter or longer? Longer. In fact, don't tell my students. It's going to be right here at 3/2 the Bohr radius is the most probable radius. If you check where is the electron now, you're most likely to find it at 3/2 of the Bohr radius. It's not the most probable, but it's the average position. So you take a bunch of measurements and you take the average. That's the most probable. We have these quantum numbers, still the same equation for energy. N, the principal quantum number, for the Bohr model, N was the only quantum number. For the quantum model of an atom, N is the principal quantum number that tells you principally the energy of the orbital. I say principally because it turns out that the M or the L's also tell you about the energy. It's not just N. If it was just N, our periodic table would look different. Because the whole idea behind this periodic table is you put one electron in, it's going to go to the lowest energy state possible. You put a second one, it's going to go to the next lowest one available. Hydrogen and helium, put 2 in. It turns out you can put 2 electrons in n equals 1. And we'll see why. The next electron is going to go into n equals 2. You put 2 in, you fill the s. You put the next 6 in, you fill the p's. So far, it all makes sense because those are all n equals 2. So now we're up to 2 plus 8 is, we put in 10 electrons. 11th electron goes into the n equals 3. 2 go into n equals 3. The next one goes into n equals 3p. That's it. You know what p orbitals are, soon. And you put in the next one until you get to 18. And then the next one does not go into the d. It does not go into 3d. 3d exists, but 3d is higher energy than 4s. And so that tells you that the L's must be doing something to the energy. It's not just the N's that are telling you the energy. That's why you have the third row does not have the middle part filled in. The fourth row, the fourth period, the scandium to zinc is filling in the 3 P's. So the potassium and calcium, that's 4s1, 4s2, and then scandium is 3d1. Because of the, now I haven't talked about what sp and d mean, but I assume you know that, and I will talk about it within the next 4 minutes. So n is the principal quantum number. It tells you primarily the energy. N can have any value greater than 0, any integer value greater than 0. So n can be 1, 2, 3, etc. Has to be an integer, comes out from our calculations, and it can't be 0, which means you can't have an energy state of 0 for an electron, for a hydrogen atom. Now, L is called the orbital angular momentum quantum number. It's telling you about the total angular momentum. So I wrote this equation on a previous slide because this replaces Bohr's quantum hypothesis. The angular momentum, the total angular momentum, has to do with L. And L can be any integer from 0 to n minus 1. So 0 is less than or equal to L is less than n. L is an integer that follows that rule. I talked about the SPDF. I have it in a couple slides more. I'll just continue on in the order here instead of jump out of order. The next quantum number, M, stands for magnetic. So the orbital magnetic quantum number, I should just use the highlighter, it's better. The orbital magnetic quantum number, M sub L, it's called the magnetic quantum number because it tells us how the energy levels are going to split when we put the atom in a magnetic field. Why does that make a difference? Because my orbital, my electron orbiting the nucleus, is a charged particle going around a circle. We've learned charged particles going in circles make magnetic fields. And so there's a magnetic field associated with that orbital. And if I put my atom in an external magnetic field, the two magnets interact. Remember, there's going to be a torque to make them align. And so the M sub L is going to tell us how close our magnetic field created by the orbital is aligned to the external magnetic field. And there's easier ways and harder ways. There's a mathematical way to show that M sub L has to be between minus L and plus L. There's also just a simple not mathematical, but graphical way. Here's a graph that's showing angular momentum. So angular momentum is distance from origin, regardless of direction. So angular momentum could be up, to the side, down. If I'm in a state, let's say L equals 2, then my angular momentum is going to be h bar square root of 2 times 2 plus 1. That's equal to h bar square root of 6. And so this radius here is h bar times square root of 6. The angular momentum in the z direction, z is defined as the direction of the external magnetic field, is m sub L times h bar. So I have 1, 2, 3 h bar. Notice that 2 squared is 4. 3 squared is 9. My square root of 6 here would be somewhere between 2 and 3. So that means that I could only have my angular momentum going like this, like this, like that, or like that. Those are the only orientations that are allowed. Now that's really bizarre because that says that my magnetic moment of my orbital can never align with an external magnetic field. Why shouldn't they? It would be the lowest energy state if they align. But quantum mechanics says it can't. Because if it did, then then LZ would be equal to L. But my LZ values are integer multiples of h bar. My total L's are not integer multiples of h bar. So they can't ever be aligned. So the L sub z is telling me the orientation. So I can actually calculate the angle between the magnetic field that's applied and my orbital's magnetic field by using the m sub L's. I guess I will begin next class period by talking about the orbitals some more. It's totally fun stuff. And it's something you really need to know if you're going to take chemistry. All right. Have a great day. I'll see you in lab mañana.